Okay, so let's move on to our lecture for today. We are basically going to continue working on number conversion, and we will be focusing on the fractions and decimal numbers for today's. Okay, those of you who came late and didn't pick up the supporting material, it's up at on that bench right there at the very back. All right, so we have a decimal number. It's 0.375. So notice it has the integer part right here. And then you also have this fractional part right here. What we did in the previous lecture, for the integer part, we would divide that successively by 2 until the remainder is 0 or 1, right? We're going to treat the integer part same way, but we're going to treat the fractional part a little different way, okay? Now, it's 0, so the binary form of 0 would be 0, right? It's pretty obvious. But for the fractional part, we're going to take the fractional part and we're going to successively multiply by 2 and take the integer part, okay? What that means is, okay, so 0.375. This lecture will require you to use the calculators, so pull your calculators if you have. 0.375 multiplied by 2, so you get 0.75. Okay, you take this fractional part again, put it here, keep on multiplying by 2, so you get 1.5 here. You take the fractional part again. You keep on doing that until you get to 0. 0.5 multiplied by 2, 1.0. Here's fractional part is now 0, so we stop here. And this is the binary code for the fractional part right here. And we actually follow this sequence right here. Okay, so 0.0, 1, 1. Okay, all right. We want to make sure that we have done this right. So we are going to convert it back into decimal. So how we do that? What was the technique that we used when we have a number in binary and we want to convert it back into decimal? What did we do? We multiply each integer, and here in this case also the fractional part, by 2, correct? Okay, so 0 times 2, 3 times 2, 7 times 2, and then 5, 2. Okay, remember your radix exists over here. So the power on this 2 is going to be 0. Okay, here, negative 1, negative 2, and this is going to be negative 3. Okay, and what do we do with these individual products? We add them, correct? Okay, so this whole thing is going to be 0 plus. Okay, I just made an error. Can anybody pick that error? So I actually accidentally put the decimal number here. Instead, I should be putting what? The binary number, which is right here. Okay, so 0 goes here. Okay, this is going to be 0. 1 gets here, and then 1 gets over here as well. Okay, all right. So this 0 times gets you 0. This is also going to be 0 plus 1 time 1 divided by 4 gets you 0.25 plus 1 times to the power 1 divided by 8. This is going to be 0.125. Okay, let's add these numbers. So you get 0.25 plus 0.125, and then we get 0.375. Which is in decimal right here. Okay, now this is actually similar to what we had over here. Okay, so we are going to treat, in case of a fractional number, we are going to treat the integer differently and the fractional part differently. There's another example. Let's move on to that. Okay, this time we have 108.265712. Again, this is being the integer part, and this being the fractional part right here. Okay, all right. I'm going to start with the integer part first, 108, successively dividing it by 2. So 2 times 54 is 108, remainder is 0. 2 times 27 is 54, remainder is 0. 2 times 13 is 26, remainder is 1. 2 times 6 is 12, remainder is 1. 2 times 3 is 6, remainder is 0. 2 times 1 is 2, remainder is 1. Okay, and we go from bottom to top, right? Okay, this being your most significant bit right here, and this being your least significant bit. Okay. So I'll just go ahead and put my binary number here, 11011 11011 dot. Okay, now I'm going to work on the fractional part. Again, you take the fractional part here, 0.265712, multiply by 2. So you get 0.531424. You take this fractional part here, put it back here, 0.53424 times 2. You get 1.02848. Take this fractional part again, 0.062848, 0.125696. I suggest that you at least carry 4 to 6 decimal digits with you all the time. Minimum 4, maximum 6. Okay. 0.125696 times 2. 0.502784 times 2. So we get 1.005568. And you see, we are looking for 0, but probably you might not get 0. It's similar to if you divide 1 by 3, you get 0.333333333, right? So how far you want to go, again, just get 6 decimal digits and that will be okay. In this case, we have 1, 2, 3, 4, 5, 6. So you can stop here. If you want to continue, you can. And then this would be 0.005568, and then you come up with some number. Okay, so I'm just stopping here. And then we know this is going to be the binary code for the fractional part. It's right here. And then we go this way. Okay, so 0.010001. Okay, so 108.265712 in decimal is equivalent to 1101100.0100001. Okay, you'll see examples very similar to this in your homework. Now, this time we again have a decimal number, but it's an octal. We have to convert octal to binary. What's the technique? Convert each digit to a 3-bit equivalent binary representation. So this should be pretty simple. Anybody remembers what's the binary code for 3? 3-bit binary code. Yes. 011. Good. All right, 7. Yes. 111. Okay. 4. 4 is 100. Decimal point. What is the binary code for 2? 3-bit binary code. 010. Okay, what about 6? It's 110, right? 110. Okay, right? Let me just write down here 011 111 100.010 and then 110. Okay. Why we were breaking it down into segments of 3? Because it's an octal, right? Okay. Now going back to octal, we have a number in binary and it's a decimal number. We are going back to octal, and the technique we're going to use, we are going to group bits in 3s starting from the right. Okay, this is our radix right here. Okay, so making segments of 3. So this is this right here. This segment is this right here, and we have 1 here which is sitting lonely. So how we can make it 3-bit? We can add 2 zeros to the left. It's not going to make any significance. Okay. Similarly, to the right of the radix, we make 3 segments. Okay, so this is right here, and 011. This goes right here, and then we have this one sitting lonely on the very right. So what do we do in order to make it a 3-bit? We just add 2 zeros to it, right? All right, and then the second step is to convert to the octal digits. So 001 makes a code of what? 1. What about 110? 6. What about this 100? 4. And that's 010, 2. This right here, 3. And then this right here makes a code of 4. Where is going to be the decimal point? Between 4 and 2. Correct. Awesome. Hopefully by the end of the term, each and every individual in this class will have answer at least once. Okay. Hexadecimal to binary conversion. Converting each digit to a 4-bit equivalent binary representation. Very similar to the example that we did above, except for we are going to make 4-bit, generate 4-bit code. Okay. So 1 is going to be 0001. 7 is going to be 0111. E is going to be, anybody remember? E. Yes. Jeremy? Correct. Good, fantastic. Okay, and then we have a decimal point here. F is going to be, F is the most easiest one, 1111. 6 is 0110. Okay, so this was fairly simple. Let's move on to the next example. There's another one. Let's do this real quick. 001. 0000. A is 1010. F is 1111, and then 0001. Okay, here's a decimal point right here. Okay. We're going to reverse the process now. Binary to hexadecimal conversion. Group bits in 4s. So here is the left part of the radix. So we start from the right. So this is this right here, and then again making a segment of 4 bits right here, which is this right here, and then this 10. In order to make it 4-bit, I'll just add 2 zeros to the left. Again, we treat the same way. The right side of the radix makes segments of 4 bits. So this is this right here, and then you have 1110, which is this right here, and this 1. How many zeros I would add here? 3, right? Okay, all right. So 0010 makes a code of 2. 1100 makes a code of what? C, 13. Okay, 1110 makes a code of E, correct. The decimal point comes here. 0110 makes 6. 1110, again E. And then 1000 is what? 8. All right, so 2CE dot 6E8. Okay, all right. Is everybody following so far? Okay, pretty basic. Okay, now in computing, particularly with respect to the memory, the base 2 interpretation generally applies. We are so much used to using a decimal number system that we understand, what kilo is, which is basically 10 to the power 3. We know 10 to the power negative 3 is milli. We know that 10 to the power minus 6 is micro. We understand that 10 to the power 9 is nano, and so on, right? In a computer world, it's a little different, okay? So this is going to be your kilo right here, to the power 10, which has a value of 1024. So the range will be from 0 to 1023, correct? This is going to be the mega, and this is M, and this is going to be the giga. Okay. Oh, this is going to be a huge number. To the power 20. Okay. So I got 104856, and to the power 30. It's going to be 1073741824. Okay. We'll do one example related to this, not today but tomorrow, and I'll show you how we can find out. When you right-click on your computer, it says space used and space available. How does computer works and find that number for you? We'll do one example tomorrow. Okay. Say you have this temperature sensor chip. Again, this is pin number 1. This is your ground, so it's connected to ground. And then this is your VCC right here. Okay, say this is 5 volt or something, and this is your V out right here. This is your pin number 14, 7. This is 8. V out. This is the V out, which is going to be between 0 and 2.5 volt. And if we have the data sheet, we can find out if the V out is 2.1 volt, how much would be the temperature, and so on. Okay, so we're going to find out the resolution again here. That's the first thing we are going to do. Resolution, the formula to calculate resolution, we did it in the previous lecture, but it's full scale range over to the power n. Full scale range is basically the supplied voltage. Okay, so say it is 2.5. Okay, 2.5 going into the DEC ADC. Okay, and it's an 8-bit ADC, so n is going to be how much? N is going to be 8. All right, so we need to find out the resolution here, which is going to be 2.5 divided by power 8. So it comes out to be 0.00976 volt, okay, or 9.76 millivolt. Okay, now what does that mean? What it means for an 8-bit, how many possible combinations? What is the range for an 8-bit ADC system? It will go from 0 to 0 to? Yes, so which would be 0 to 255, right? Let's do it here. What is going to be the range for the 8-bit system? It's going to be 0 to the power n minus 1. So it will go from 0 to, n is 8 in this case, so it will go from 0 to 255. So what that means is, if it's 255, it in decimal, it would refer to 2.5 volt, because that is what you are providing over here to your ADC. At 0 decimal, it's going to refer as 0. Say you're getting 0, okay? 0 would corresponds to 0 volt. So what would be an 8-bit code generated by the ADC for 0 volt? All zeros, right? 4 zeros, 4 zeros. Okay, so say your temperature sensor is reading 0 volts. Okay, that 0 volt goes into 8-bit ADC. What comes out? It comes out 4 zeros, 4 zeros. Correct? Say if the voltage here is reading 0.00976 volt, what is going to be the code here? 0.00976 volt is when it's 1. What is the 8-bit code for 1? It's 4 zeros and then 0001, correct? Right? What would be the code at 0.02? So if you multiply 0.00976, multiply by, if you add 0.0096, it comes out 0.02. So that would be what? 0000010, right? So that would mean 2 would be 0.02. Yeah. So what I did here, moving from 1 to 2, I'm going to add 0.096 to this number, so I get 0.02. And I move to another level, 3, so I add 0.02 plus 0.00976, I get 0.03. So at 0.04 volt, if it's reading 0.04 volt here, what 8-bit code it's going to generate? 4 zeros and then 0, 1, 0, 0. Is that what you're saying? How many of you guys think that's right? Right. Because if 3 is 0.03, then 4 is going to make 0.04, correct? Approximately 0.04, which would refer to an 8-bit code of 4 zeros and 0, 1, 0, 0. So if it's generating a voltage of, say, 2.2 volt, okay, which goes into 8-bit, it's going to generate a code of 1110 and then 0001. That is what comes out of the deck, ADC. 1110. 0001. That goes into your microcontroller, and there's a way for us to go into our microcontroller and do the coding and say if T temperature is less than 23 degrees centigrade, if this is true, then turn the heat on. Okay, this is your memory block right here. Okay, everything that goes into the microcontroller, obviously we can save it. Usually we are dealing in hex because we don't want to write so many binary numbers. So what is the hex code for this 11100001? 1110 is E, correct? And then 0001 is what? 1. Okay, so this can be stored in memory as E1. X, okay, and if I say FF here, what does this mean? So your memory have two addresses. One is the location address, and the other one is carrying the data. So this is your data even, and it's stored in memory location which is FF, correct? Okay, this is probably more information than I'm providing that you need at this point, but this was the whole. This is how, you know, the digital system, this is how it works. We are moving to digital arithmetic. We're going to do some binary addition, multiplication, and subtraction also. Okay, so we got 2 bits A and B. So 4 possible combinations: 0, 0, 0, 1, 1, 0, 1, 1. Okay, when we are adding A plus B, and both are set to 0, so 0 plus 0, sum is going to be 0, carry is going to be 0 as well. Okay, 0 plus 1, sum is going to be what? 1, and carry is going to be 0. 1 plus 0 is sum is going to be 1, and carry is going to be 0. 1 plus 1, sum is going to be 0, and then carry is going to be 1. Okay, cool. Say if you have 3 bits and they all are set to high, 1, 1, 1. What would be the sum now? Okay, sum and carry. Carry is also going to be 1. Okay, so just remember this, and you should be able to verify your answers. So we have 3 examples here. We're going to start with this one on the right. The technique that you would use is add the individual bits and then propagate the carries, okay, as they go on. Before I start, I just want to give the weight to individual bit. This is 1, this is 2, this is 4, this is 8, and this is 16, okay. So if I ask you what is the decimal equivalent of this number, what would that be? Come on. You just add the values, right? All the weights for which the bit is set to 1. So this is 1, which is 16. 16 plus 4, 20. 20 plus 1 is 21, right? This is in decimal. And what about this one right here? 16 plus 8, 24. 24 plus 1, 25. So we will get 46 here, okay? All right, let's start working on this thing now. 1 plus 1, sum is going to be 0. Carry is going to be 1. 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 1 is 1 plus 1 is 1, 0, right? Correct? Okay, all right. Again, I'll just write down the magnitude of each bit. 2, 4, 8, 16, and 32. Okay, so 32 plus 8 plus 4 plus 2. So you get 32, 8, 40, 40, and 46. Okay, so these two actually match, right? Okay, pretty simple. Okay, we're gonna move on to the next part. Was everybody following this? Any question? Good? Okay, all right. Yes. It's not 1, it's actually 0. This is the carry right here in the table, okay? Why this is 0? Is that what you're asking? This one right here? Okay, so if you have 1 plus 1 plus 1, the sum, yeah, it's 3. Yeah, so you get 3 bits right here. Okay, say this is C. No, that's a good valid question. Say this is bit C, so you got 3 bits. And then if you add all 3, these are the 1, 2, 3, 4, 5. These are 5 possible combinations that could happen, when you are adding. So for all these combinations, these are the sums and carries. Okay, let's move on to this part right here. We're gonna have to convert it into binary first, and because it has a base of 16, so I need to make segments of how many bits? Our previous lecture, so B was 1011. Okay, 1011. Okay, and then dot 1, so it will be 0001, and then A 1010. So F, this right here, E 1110, and then A 1010. Okay. Okay. Now I have to fill a few zeros here just to make it even. So what I do here, I'll just add zeros here. Okay. And then I'll just add zeros here also. Okay. Remember, this is your BF dot 1A, and this is your AEF. Okay. All right. It's a big number. Okay. 0 plus 0 is going to give you 0. 1 plus 0, 1. 0 plus 0, 0. 1 plus 0 is 1. 1 plus 0 is 1. And the rest of them are going to be 0. Decimal point right here. 1, 1 is going to be 0. You got this carry. 1, 1, 1 is going to be what? Sum is going to be what? 1, right? And then the carry will be 1. 1, 1, 1. Sum is 1. Carry is 1. 1, 1, 1. Sum is 1. Carry is 1. 1, 1. Sum is 0. Carry is 1. 1, 1, 1. Sum is 1. Carry is 1. 1 plus 1. Sum is 0. Carry is 1. Then 1, 1, 1. It's going to be 1 and sum carry is 1. 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 0 is 0. And 0 plus 1 is 1. Okay. You go. Awesome. Crazy, huh? So, okay, moving on to the next one. Okay. 0 plus 1 is 1 here. 1 plus 1, 0. Carry is 1. 1 plus 0 is 1. 1 plus 1, sum is 0. Carry is 1. 1, 1, 1. Sum is 1. Carry is 1. 1 plus, this is going to be 1 and this is going to be 1. Okay. All right. What is the decimal equivalent of this number right here? 1, 2, 4, 8. This is 0.5. This is 0.25. And what is the magnitude of this thing right here? 125, correct? Okay. So what is this number right here? 11.25. So 8 plus 2, 10. 10 plus 1, 11. 0.25. Okay, what is the decimal equivalent of this number right here? 1 plus 2 is 3. And this is 0.25 plus 125. 0.3125. Okay, so if you add these numbers, plus 0.125, sorry, 0.375. Okay, 3.375. So you get 14.625. Okay. It would be actually also nice to get one eraser for you, and I should get one also. Right. So 1, 2, 3, 4, 8. This is 0.5 and this is 0.125. Okay, so adding these numbers, 8 plus 4 plus 2 plus 0.5 plus 0.125, and that gives you 14.65. Okay, and that matches with this number right here. We just verified what we did. We get 8 minutes more. Any questions so far what we have covered? Shall we move to the next example? Okay. Okay, multiplication is probably the easiest among all the other operations. So again, for 2 bits, 4 possible combinations. 0, 0 is going to be 0, 0 times 1. Any of the inputs 0 is 0, and then 1 times 1 is going to be 1. Okay, we're going to start off with this. 7 times 5, we know this is going to be 35. Okay, I'll start with this right here, and because of its position, I'm going to have to add 2 zeros. 1 times 1 is 1. 1 times 1 is 1. 1 times 1 is 1. Moving on to this one. Because of its position, I'm going to have to add 0 here. 0 times is all going to be 0. And then 1 times 1 is 1. 1 times 1 is 1. And then 1 times 1 is 1. Okay. Let's add these numbers. 0, 0 plus 1 is going to be 1. 0, 0 plus 1 is going to be 1. 1 plus 1 is going to be sum is 0, carry is 1. 1 plus 1, sum is 0, carry is 1. And 1 plus 1 is equals to 1, 0. Okay. Here, let's verify we got the right answer. The magnitude for each bit, 1, 2, 4, 8, 16, and 32, right? Okay, so we add these numbers, so we got 32 plus 2 plus 1. So that gives us 35. Again, matches. With this right here. It's just how you do the multiplication in decimal. You exactly do the same way. What I did here, I started off with the most significant bit here, okay? And because it's sort of like in decimal, it represents the 100th value, right? So I'm going to have to add 2 zeros to it, correct? And then 1 times 1 is 1, okay? 1 times 1 is 1, and 1 times 1 is 1, correct? Now this 0, I'm moving to this 0 now. This represents the 10th, right? So I'm going to have to add 1 0 here. 0 times 1 is 0, 0 times 1 is 0, and 0 times 1 is 0, okay? And then this 1, it's just unit, so 1 times 111 is going to be 111, and then you add these individual bits together, okay? Using this table right here, okay? All right. There are multiple ways of doing it. If you start with this bit, you change the order then, okay? Depending upon whichever way you do it, whichever way you learned in high school, you just implement that. This is one of the way of doing it. You can do it in multiple ways, okay? Everybody understand this part? Shall we move? Okay, all right. Okay, last topic for today, it's binary subtraction. So I already had this filled. Here are the differences and borrows. 0, 0 is good. Difference is going to be 0. 1 minus 0 is going to be 1. 1 minus 1 is going to be 0. 0 minus 1, difference is 0. Borrow is 1. Okay. So this is 13 minus 10. And this is the code. We know that this is going to be 3. Okay, in decimal. Let's see if we get it over here or not. So 1 minus 0 is going to be 1. Okay. 0 minus 1, this means we're going to have to take a borrow here, right? So I'm going to move this 1 to over here, and this is going to be 0. Okay, now 1 0 minus 1 is going to be what? Say it again. 0. 1 0 minus 1 is going to be what? Yes. 1. You know why? 1 0 makes a code of what? 2, right? 2 minus 1 is 1. Correct? Okay. 0 minus 0 is going to be 0. 1 minus 1 is going to be 0, right? Now, this is the weight of these individual bits. 2 plus 1 is going to be 3. Correct? Okay. Now, let me go back. So, moving on to the second bit. When I was doing the 0 minus 1, because 0 is smaller than 1, I had to take a borrow from the next significant bit, which was 1. When I borrow this 1, this turns into 0, right? And this 1 goes here. It's actually side by side. It's actually 1 0. Okay? 1 0 makes a code of 2, correct? Right? And minus 1, 1 0 minus 0 1 gets you 0 1, right? 1, which is in decimal, it's 1, correct? So that's how I got 1 here, right?